think it's, yep. Okay, sweet.
Okay, so I'll just give a brief intro and then you can
Sure.
go ahead. So hello and welcome everyone. This would be our last STEMinar for fall 21. And we have with us today Arvind Aradhya, who is going to be talking about spectrum sharing. And he has quite an interesting tagline, I would say, for his topic, which is linking the cat's eye nebula, raining cats and dogs, and cat memes. So we welcome you to the world of spectrum sharing. And I'd promptly hand over the mic to Mr. Arvind Aradhya, and you carry on with your talk.
Cool. Thanks, Tanmay. Thanks, Sarah and Valerie. It's a nice opportunity. I've been wanting to do this for a while, and I nearly didn't do it, except thanks to Sarah and Valerie's persistence. But yeah. So basically, yeah, I'm a PhD student in the EC department at CU Boulder, and I started here in the spring of 2019. So I'm in my third year now, just finishing up my third year. And this is a project that I just got involved with basically about a year ago, in essence, and then in earnest only about 6 months ago. So a lot of this is just going to be overview. And what it is looking at ways for passive and active users of the spectrum to coexist of the radio frequency spectrum. I'll get to what all that is in a second. But yes, so this is my RA work, essentially, and I've started doing the research on this and hopefully it leads to a PhD thesis. So there's still open questions as to what I'm actually doing, but I'll illustrate all that stuff as I go ahead. So in terms of the tagline, that's a pretty long tagline that I had, which said linking the cat's eye nebula, which was this. Nebula is just basically a cloud of gas and dust in space. It's hanging around a star, and they're really pretty to look at. If you've ever gone stargazing, you should. We have an observatory on campus, so that's something that is accessible to everyone at CU. And this is one of the more famous and picturesque nebulas here. So you got a star in the center. Let me bring up my pointer. Here. So you got a star in the center, and that's basically lighting up all this cloud of gas and dust, and then that is radiating in emissions. And this is probably a false color picture. It's not exactly how it looks to the eye, but that's what they are. And so that was one part of it. So what's the connection between the cat's eye nebula, the raining cats and dogs? This is just an image I took. Apparently, if you Google raining cats and dogs, this is the first image you get. It's a Library of Congress thing saying unpleasant weather. So that's just a metaphor, sorry. And then the last one is memes, cat memes, right? Which basically, I don't know if you could causally say that this is what led to social media or the other way around, but yeah. And this particular meme that I made is talking about download speeds. So the link between all of this is that they basically rely on the electromagnetic spectrum. So this is a radio telescope, and that radio telescope essentially is what allows you to image stuff like the nebulae. This particular picture is an optical image, so it's not a strict analogy, but radio telescopes also do perform astronomical imagery. So if you recall the news about some time ago, about 6 to 8 months ago, or even longer than that, we had the first ever picture taken of a black hole with using something called the Event Horizon Telescope, which is a telescope that was actually the size of the Earth. And I'll get to that again in a bit as well. But yeah, so they are used for imagery, and then they operate in the radio wavelengths, hence radio telescopes. Raining cats and dogs. The link with that is, of course, any kind of weather monitoring that we have, satellite-based weather monitoring, looks at the Earth in the radio frequency wavelength. So I'll get to what that exactly means in a second, but basically what you can see here is that we have your brightness temperatures of the ground and the cloud. It's like an integrated column. So if you look at any particular pixel here, then it's essentially looking at the content of water vapor that's there. And the way it does it is it looks at certain radio emissions from the Earth, and then it can establish how much precipitable water vapor and how much of at what height it is, and so on and so forth. So that's basically the technique is called microwave sounding for one of them. Of course, they do that in infrared, they do that in optical, but radio is really, really powerful and used for the numerical weather prediction that models that run, which allow you to forecast weather. And then, of course, all communication, nearly all communication nowadays, wireless communication uses the electromagnetic spectrum. So the connection between all of these three things is that they are all users of the electromagnetic spectrum. And for our purposes, we will be restricting ourselves to the radio frequency range, which is, anything above, anything in the region of kilohertz frequencies and so on. So it's an electromagnetic wave which is characterized by a frequency and a wavelength, and then anything in that when one particular frequency range is called radio. And there's a chart later which will correct me if I made a mistake in that number. But yes, with respect to what we're actually seeing, so here, at least for these two, for the passive uses of radio spectrum, where the emission and the signal and the image that you're actually looking at is something natural. So what you're doing there is you're actually looking at actual physical processes. So here I've illustrated two kinds of things, which is one is line emission. So you have any particular, any substance that's comprised of matter, and you say you have electrons in that matter, and then these electrons are transitioning between various energy levels, and then as they transition, you have emissions of light. Now there are certain frequencies which correspond, so certain energy levels which correspond to a transition energy difference, which then corresponds to that particular phenomenon emitting photons in the radio frequency. So that's what you talk about when you talk about line emission. So sometimes you have these nebulae, particular lines are present because you have particular gases. So for example, you might have oxygen in this, and that's excited, or it's warmed up by the light, and it absorbs light from the star in UV and so on, and then it re-radiates that. And that's in a particular frequency or a line, or a very specific frequency, which is what's called a line, and that's your line emission. And then, so that's one kind of emission. And then the second kind of emission is you have just continuum emission. So this is quantized, which is why it's called line emission. It's only at very particular frequencies, and this is continuous across all frequencies. So if you heat up a light bulb, what you're seeing there is continuum emission from say incandescent bulb. If you look at yourself in an infrared camera, you will be glowing because you're emitting infrared radiation, and this is essentially just power that's being transmitted by the object by virtue of its temperature. So it's just the black body. This is black body radiation. So that's a pretty much basic primer as to the kind of emissions that are there. And a lot of objects, if you look at this black body curve, the peak emission is dependent on the temperature that you have. And that temperature essentially dictates where most of the frequency, is. So the sun, for example, has its photosphere temperature is about 6,000 Kelvin. So it's most of the energy that's coming out from the sun, most of the light energy coming out from the sun is coming out in the form of visible and a little bit in infrared. But if you go down in temperatures, something like, usual temperatures, so 273 Kelvin, 290 Kelvin, and so on and so forth, then that stuff tends to be brighter in the radio regions. Because you look at this, it's a kind of a fraction. This curve is a fraction, and you see it flattens out and it moves to the left. It moves to the right, and the wavelength increases. So that's how you get more radio emission at far, far lower temperatures. So essentially the point of all that to say was you have various objects, at least for Earth remote sensing, cloud tops, actual gases, atmospheric gases in the atmosphere, so ozone and so on and so forth, are all emitting in radio just because they're at a non-zero temperature. And that's what we would observe, and that's what we would like to see. Now, of course, the problem comes in with interference. So interference, and this is, by the way, the frequency spectrum that I'm talking about. So radio is basically anything from here on. So with a wavelength of 1 centimeter to about 10, and further on, but millimeter wave onwards is basically radio. So yes, what's the problem with this, and why can't we just coexist? Of course, the reason is interference. And quick primer on interference. First of all, can anyone read this? There's text in that image. Can anybody read that? Just curious.
I think I see an S.
Is it Swift?
Yeah, it is actually Swift. So I'll get to that in a second. But basically what interference is if you have we all have daily experiences with what interference. If you have two people talking at the same time, in close proximity, then the information content of what's actually being delivered to your ear is not discernible. And similar, is the case with electromagnetic waves. So if you have two waves at a certain frequency, then they tend to add up. It's linear superposition. There is a little bit of math here, but basic math. So V1 and V2 just represent sinusoidal waves and the signals, which is the general form of electromagnetic wave. The frequencies are the same. Then essentially what you've done is you've added the amplitude, and there's no unique decomposition into, if I just tell you that this is what you're detecting, there's no way of you saying whether it was V1 and V2 or twice V1 and half V2 or something, because the terms just fuse together. And then that when we want to make out what signal was actually delivered and at what frequency, we do this thing called a Fourier transform, and then you look at the amplitudes of the various components, and then that tells you the information of which frequency had what information content and so on. It's essentially looking at the spectrum. And that tells you the information that you do need, whether it's encoded, whether it's natural information. You need to be able to do this decomposition in order to actually be able to extract information from that. So the picture, coming back to that, is something interesting, is that here it's the same kind of interference, but with light. The people, I do this because I'm color vision deficient, or apparently I'm supposed to be color vision deficient, but so for me, I can make out Swift pretty easily in this one, but in this one, it's a little harder for me to make that out, because apparently in my case, my eyes tend to treat, even though the colors, the frequency of light corresponding to the colors that spell out the letter Swift, and then the colors that are the background are different, my eye tends to perceive them as the same, and then that leads to this kind of interference, and then I'm not able to tell the text. So this essentially is exactly the same process. This math is exactly the same process that happens with interference in electromagnetic waves. And the interferers here are active transmitters. So things like radar, things like your phone, which are actually sending out electromagnetic waves, they tend to populate the same space as the emissions that are coming in from space, and then everything gets mixed up at your receiver, and then you're not able to tell which is what. And this is primarily a problem for the people who are doing the passive observations, such as radio astronomy and so on, because the signal strengths there are so much weaker, because these things are coming from light years away. And for Earth remote sensing as well, if your satellite is looking down at the Earth from an altitude of 36,000 kilometers, any signal that gets up to that, it's the inverse square law. And also you have a thing called the Friis transmission formula. And then through that, you basically reduce the power that's, with distance, there's a reduction in power. And passive stakeholders, so people who use the passive spectrum, are almost always disadvantaged by any kind of emission. And that's what the entire research project is about. So all of this was context, and our objectives of this project, I'm involved in two projects right now. One is called CU, which is University of Colorado, passive active spectrum sharing, which is what I've been talking about, and also something called the National Radio Dynamic Zone. So that is something which is being instituted by the NSF, the National Science Foundation, who's funding these two projects. And then the idea there is to establish a physical zone around sensitive facilities, so around a radio telescope, for example, and have the spectrum sharing be more efficient than just cordoning off areas for all time. The current way that people divide up the spectrum so that two people aren't using the same spectrum and causing interference, the current way that that's done is everybody who's using spectrum in some frequencies has to obtain a license from the FCC, which is the Federal Communications Commission. And then that license is what allows you to transmit in that particular region. And there are certain regions of spectrum which are kind of protected for use by meteorology, for use by radio astronomy, for use by communication. So there's parts which of the spectrum where you can't use because that spectrum is being used by the military, for example, and you can't transmit with commercial mobile phone communications in that region. So National Radio Dynamic Zone, the word dynamic refers to the fact that they are not allocating some frequency from now till for all time to come. They're saying that we will give you this frequency when you need it. So there's this is called time division multiplexing, where I let you have the lease for that spectrum for about an hour, and then once you're done with it, then somebody else takes over. So then the idea is that this obviously is more efficient than saying that I have access to this particular spectrum for all time to come. So they want to institute this because with growing needs for communication and growing needs for weather monitoring, and there is both these stakeholders are coming closer to each other, and then they're causing interference amongst themselves. So that's the overall mission. And currently, we're actually liaising with the one facility called the Hat Creek Radio Observatory, which is a radio telescope out in California. And I'll show you that stuff later. But this is our particular task right now, is to just monitor the background. So basically, put up listeners everywhere and look across the spectrum in the frequency range we're interested in and see what the current baseline is. And the idea for that is we will establish, a background activity and say, okay, this is what quiet is circa 2021. And then going forward, if the FCC has to issue licenses, we have to make sure that whoever's obtaining a license, who is requesting a license, will always transmit below that noise, or when they're not supposed to be transmitted. So that's the idea of the overall infrastructure that we're developing to actually do this. And the reasons. Primarily, in some confessions here are that technically it's not an unprecedented, or it's not like something that we need to discover a new physical phenomenon, or so on and so forth. It's very much an engineering problem, and more than that, a couple of conferences I've been to actually talk about it as a policy problem. So it's not that people don't know what to do to avoid interference, but there's also a lot of disagreement about terms and disagreement about who gets what and so on. And that's where the morass actually is. So these are the kinds of issues that are outstanding in the area, and I'll get to more of them in a second. One thing I do want to draw your attention to is the out-of-band emissions. So this is something I'll talk about if it's a little hard to understand why interference occurs, even when everybody's playing according to the rules. And then, of course, once we do this and once we detect interference, then there's various methods of mitigation. This is kind of a block diagram overview. This is what I was talking about. Any signal. So this is if you hook up like an oscilloscope to your antenna, you see a voltage versus time, which is the signal that's actually induced in your electronics, and that signal can be decomposed into various frequency components. This is done using a Fourier transform, and then you look at the Fourier transform over time, and then you can make out, okay, this is at a certain time you had a peak at a certain frequency, and at another time you didn't have something, and then you basically establish a spectral occupancy footprint, which says, okay, this particular signal needs this entire region of the spectrum to exist, and nothing else should exist in that particular region. And then again, you have radio telescopes, you have weather monitoring satellites, and then you also have natural sources of radio emissions. And I'll show you guys what lightning does in a second. And then you have your communication satellites, communication base stations. And then essentially you have what we have are software-defined radios, which I'll show an image of, which is basically a radio. It's like one of those transistor radios that people used to own when I'm dating myself. I'm a 90s kid, so we had actual radios, and at least we had radios on your mobile phones, and then FM radio. And then it's essentially that, but the difference with this is the software-defined prefix means that there's a lot more processing that I can do, and it's not restricted to just a particular frequency range. I can tune it to a lot wider frequency range, and all that tuning can be done using programs and scripting on a computer. And this is just an interference pattern. So what I would like to illustrate here is that when we're doing this across the Earth, so if you have various locations of interest, then there are various things that come into play. So you have signals that bounce off mountains, and in Colorado, people would have experience with this. If you go up into the mountains or the hills, you just tend to lose signal reception because you're in the shadow of a tower, you're in the shadow of a hill, and there's no signal that's getting through to you. And that's insidious enough. But there's also the fact that when you have reflections, you can have constructive and destructive interference. So you drop 2 pebbles and they produce their own ripple patterns, and then that causes a spike in the water level at one point in a trough. So if you have a trough at some point, then that essentially means that you're not getting any signal strength. So this is called multipath, and it happens all over the place. So if you're especially in say an urban environment where you have high rises, every flat face of a building acts like a mirror to an extent, and then it bounces signals off, and then you get something complicated. So there's a lot of studies on modeling that, and we need to be able to, so analytically figuring out which particular region is free of interference or is susceptible to interference would involve a lot of this modeling, and that, as you can imagine, gets really computationally intensive. And not that people don't do it, but we would also like to ground truth those simulations with actual measurements, and this is one of the tasks that were taken up at CU in order to actually quantify the detected noise floor at various locations. The second thing that we want to do is, once we actually detect interference, we want to be able to figure out where it is. So what this is these are the software-defined radios that I told you about. So this is a telescope that we're trying to protect, and this is a GPS satellite. So GPS satellite gives you a clock, essentially. That's what it's transmitting. And once that clock comes over, we use that as a really precise time standard. We send that time standard on to your different software-defined radios. And what we do, I'll play that again, is we record the arrival time of a particular wave. So if you have your mobile phone tower here that's transmitting a signal when it's not supposed to, so you basically measure when it arrives at different radios. So in the pink radios and the yellow radios and the white radios. So you have a signal that's emitted, say, somewhere here, and then it reaches after a certain time delay, because finite speed of light, and it takes a certain time for it to propagate from here to here. And then what you do is you do something called cross correlation, where you basically slide those two waveforms against each other, and then you integrate, and then you get a peak whenever the waveforms overlap with each other exactly. And then you know how much you've slid it by, so that tells you the time delay that actually exists between the transmitter and the receiver. And you do that for all of these different radios. And between any two pairs of radios, which are color coded in the same color here, you have a constant difference in arrival times. And if you solve the math for that, you get a hyperboloid, which will construct a hyperboloid on the surface. So this yellow curve is the possible location in the tower as determined by just the two yellow radios. And then similarly, you have a white hyperboloid, which is for the proud location determined by the white radios. And then you have the same thing with the red. And then wherever they intersect, and they will intersect if it's a genuine signal, because the math works out that way. And then what you end up having is being able to say where this particular source of interference came from. And that's really useful, because if we're monitoring these radio stations, sometimes it's static stations, but sometimes, and at HCRO, this was a problem, Amazon delivery drivers and people who came in who had their phones on, they could be anywhere. They could be delivering to the neighbor or the neighboring farm or something. And then we need to know where that source of radiation is coming from, so that we can then take appropriate measures. So that's the second goal. So the first goal is to quantify it and make sure that we have traceable measurements, and say, okay, this is the noise floor and it's X watts of power per hertz. And then second thing to do is we want to be able to localize these things. And they involve a little bit of different hardware. This would need us to have a really precise clock and all the associated hardware with that, but basically all of it is still done through software-defined radios. Then if I keep going, so this is the setup we have on campus. So these things you see here are just software-defined radios. They're about credit card size. All they have is, I'll show you a block diagram in the next slide, but all they have is an analog to digital converter and some amplifiers and some filters. And then you tune them to a particular frequency, which is essentially how you tune to a particular radio station. And then they record the waveforms. And then they're all hooked up to Raspberry Pis here, and then that's sending our data to our server. And this is an antenna that they're all hooked up to. So this antenna is the antenna that actually looks at the electromagnetic waves and then translates them into your voltage waveform. This is set up on top of the engineering building, which is a great view, by the way, if anybody's ever up there. And this is the block diagram I'm talking about. So the antenna is the white pole that you saw earlier. we have a switch, and if anyone's interested, I can get into why we have reference temperatures, but basically it's for calibration. And then you have a low noise amplifier, and you have a mixer. This is called heterodyning, and then you send it through a filter, and then once you get that particular frequency, then you basically get your data, and then we do all our processing. Not really much. And this is how it looks inside for our radiometer, with your hot reference and your cold references, and then the rest of it is just components. Just putting that there for scale. So these things are about, you can see my hand in the picture, but yeah, that's about how big they are. And then this is what we did. This is an example survey that we actually carried out. So again, if you've lost a train of thought already because I'm rambling too much, what we're trying to do is we're trying to look at who's occupying a certain spectrum at any given time, so that we can then build up the infrastructure to say, okay, you have it from 5 to 6, you have it from 6 to 7, and so on. So what we did do, we looked up the Amazon Web Services uplink channel, which is operating on this particular frequency, and these are all the other parameters that you have here. So frequency, bandwidth is basically how broad that the footprint that I was talking about earlier, and what that signal occupies in this frequency space. And then some other specs. What we did do is we recorded for 1 second every 30 seconds. So we just recorded a 1 second burst at intervals of 30 seconds. And this is a problem because it generates a really big size of file. This is just for 1 second. And then if you do this over weeks, you already get gigabytes and terabytes. So that's just illustrating it. This is what it looks like. So what we have here is this x-axis is actually time of day, and then the different colors are the noise as monitored on different days. And so there's interesting stuff you can see here. You can, for example, you can make out like there's a peak in traffic, or there's a peak in whatever's being transmitted between 5 and 6 on a particular day. So again, color coding, but I guess that's Wednesday. Yeah. So Wednesday between 5 and 6 is there's a peak. There's a short burst. We don't know if that's noise or if that's a legitimate transmission, but around those times. And then you can actually see that during different days have different patterns, and you can kind of correlate that with people and how they're actually using the network. So that's the third leg of the tripod, which is the active users. And then based on when we need more spectrum, we can then structure around and schedule other observations when, for example, here between say 1 and 7, there's not many people using the spectrum. So we could probably be like, okay, radio astronomy and remote sensing can have this particular time. And yeah, so that's essentially the concept of this. Actually, let me pause sharing. I also want to show you before I resumed with this is mentioned lightning, and there's a really cool illustration of how lightning is also one of the emitters. And let me share this. So I think you can see. So lightning is basically a transient current. Any transient current produces electromagnetic radiation. So this is a live map of lightning strikes. So what you're seeing here, and this is for this localization that I talked about, is it's basically doing the same thing. All your spots here in blue are lightning monitoring stations, which is similar to the station that we've set up. And suppose you have this is Murphy's Law. I swear they were striking really. Okay, so there you go. So that strike that you saw there happened somewhere in Central America, Latin America, but it was picked up by all these stations. And this is that hyperboloid map that I'm talking about. So lightning is one of your intermediate interferers, and it's a natural source of interference as well, which could it's generally tends to be outside the frequency range for radio astronomy, but it does interfere with say for low frequency communications like the Navy uses, because low frequencies travel further. As you can see, stuff that's happening in Europe can be detected in North America and so on. So yeah, let me go back to my presentation and also look at the time. Sorry, let me share again. Stuck. Any questions, by the way, until now so far on whatever? Any comments, questions?
That's a really cool map. I didn't know there was a live lightning map for the whole world. That's really neat.
I mean, I'll share the link with you guys later if anybody's interested in that stuff. I actually interned at a company in Louisville. One of the companies making this is in Louisville, so local. So yeah, coming back to what we're doing, there's a citizen science component of this as well. So this is something that I coded up on my phone. This is just Google Maps on my phone. That's a screen recording, and I'm walking around campus. Well, not that fast. This is sped up. But basically, what it's doing is it's looking at the RSSI value, which is the received signal strength indicator, which you can look at on your phone, and it's plotting that versus location. So, and then this is an app that I used to make that. It's called Automate, and pause, and next slide. So that looks like this. So this is another map. So basically what this is it's just saying, okay, wherever I went, obviously I was only on biking trails or running trails, there is, certain amount of signal strength. And you can see variation because of the multi-path stuff that I told you about. So this is something that we're interested in looking at, not only for the mobile frequency regions, but for other regions as well. So you could do this on your phone and you could plot it. So that's just one thing that I want to highlight. And then some other questions that we're tackling. A lot of this is just jargon, but basically outstanding issues that we want to tackle. We've moved beyond what I'm doing specifically to what the group is doing. And there are people looking at the policy aspects. There are people looking at, economic incentives and trying to figure out, how to intervene so that maybe, passive spectrum sharers can, lease their spectrum when they're not using it and get paid for it and so on. So there's already, there's precedent. They identify different kinds of interference. So people would have heard of Starlink and, the internet constellation. And then what those satellites use to talk between themselves is a frequency that's being used by remote sensing. So that's another source of interference. But that's interference between, say, a new entrant and an incumbent. And we have interference between new entrants and between existing users and other existing users. Perhaps one of these examples was GPS, the actual GPS system that we use, versus another communication service provider called Ligado, who had a throwdown essentially with the Department of Defense because of all these issues. Basically, the problem is, like I alluded to earlier, no one agrees on definitions, and no one trusts each other. So this is essentially what happens. I said earlier, I'd talk about why interference actually happens. It's something called out-of-band emission. And what out-of-band emission is if you take any active device. So I don't know how familiar people are with basic electronics, but you have passive components, which are resistors, capacitors, inductors. They don't actually need power to be supplied to them for them to operate. But you have other devices like, say, a transistor, which is something called, it's an active device. So you need to give it power, and then you supply a signal, and basically you're giving it a power signal and you're giving it your actual voltage signal, which you want to modify in some way. So active devices have this characteristic of something called intermodulation. So if you decide to sum two voltages, say in a diode, what actually happens is there's an exponential relationship. So the sum actually occurs in the exponent. And then if you remember a Taylor series expansion, what that does is that gives you square terms and cube terms and so on. And then because these are trigonometric, these square terms and cube terms essentially result in an addition of frequencies and a subtraction of frequencies. And so what you're thinking of doing is, if you had an active transmitter, let's say I'm authorized to transmit at 100 megahertz, and I do all my due diligence and I actually build a system that transmits at 100 megahertz. But despite all my efforts, because of this nonlinear modulation that happens, there will be certain harmonics that they're called harmonics because they occur in multiples of the frequency that we're transmitting. So if I'm licensed to transmit at 100 megahertz and I kick up my transmitter into full power and I amplify my signal, then I get some signal at 100 megahertz and I get some at 200 and 300, and the power level drops. It's much lower than what I'm supposed to be transmitting 100, but there's still something called out-of-band emissions, and that's the problem here. So Ligado This is the light squared signal, which is the signal power for the proposed system. And then this is the power above which GPS has problems. If you transmit in this entire region that's covered by the blue curve, you end up having issues with actually localizing your location. And naturally, if they're occupying the same spectral region, then you essentially have interference. The problem with that, I mean, again, standard problems are all this, that first of all, this is one of the reasons why you're not allowed to turn your phone on in an aircraft, because even though it's very unlikely, there is no exhaustive evaluation of every particular phone manufacturer and every particular aircraft radio. That's just not feasible. There are too many products out there. So by necessity, the FAA defines an interference power for avionics and says, okay, it should be certified to withstand that particular power, particular level of interference. But and then when you have problems when you move that over to some other system, because whatever can be tolerated by aircraft may not be tolerated by something else. And essentially, it's like a case in pretty much every other field. It's a case of regulations not actually catching up with the technology, or in this case, people not agreeing on various different ways of talking about the same thing. And this is another illustration of the same thing. And here, Ligado wanted a standard that actually graded GPS, whereas the conventionally accepted standard was something different, and then that just led to problems, and it was lawsuits and so on. So our idea with this is if we can establish traceable measurements. So we're in Boulder, so everybody should actually know the phrase NIST traceable, because that's what NIST does, and it's right here. You establish certain standards and certain methods of measurement, and then you tailor every other measuring device to that particular standard. So in our case, it would be tailoring the voltage and the power that we actually measure through our antennas to something that's measured at NIST and says this is the absolute radiometric brightness or the absolute power that's transmitted at a certain frequency. And once we do that, and once we achieve that, which is probably what my PhD is going to end up being about, is building that system. But once we do that, you essentially can negotiate all these problems and say, okay, this is the absolute stuff, and this is how much it is. And then we build up from there with already existing theory and analysis. And then there's more stuff that we're doing, right? So there's, I talked about the Starlink satellite and how they're actually causing problems for remote sensing. But at the same time, as Homer Simpson's pointing out here, it's an opportunity for actually conducting more measurements. So imagine that your signal here, this particular, oh, you can't see my pointer. Imagine that this particular satellite is your remote sensing satellite, which is looking at signals from the Earth. And this is GPS satellites themselves interfering with something that needs GPS itself. So it's a whole complicated web there. This satellite needs GPS to operate, but GPS causes interference. And so what they do is then they're like, okay, let's not look at our own frequency spectrum. Let's exploit the GPS signal. So what they're doing is they're looking at the direct signal, which is obtained by positioning, and they're looking at the same signal which reflects off the Earth and comes in after a certain time delay. So then, which is the same math as it was before. And this then allows you to pinpoint where it reflected from, and the power levels that it communicates will then tell you what actually happened at the point of reflection. So they've turned something that was initially never meant to be used as a measurement signal or an active probe of the environment into something that is easily used to actually perform environmental measurements. And then the refracted signal then gives you, because this is passing through the atmosphere and bending, that then tells you properties of the atmosphere. So this is exploiting the communication signal for actually conducting the same kind of measurements that we have. So this is another area of research that we're looking into. When I say we, obviously, I mean the group, but looking at different statistical methods to kind of remove this interference from what exists, and also looking at the physical interaction between these signals. So say, for example, reflection. So ice, one of the most common things is when you reflect something, it polarizes, or it gets polarized. So if you have an unpolarized transmission coming in and then it reflects, then you have a polarized signal coming out. And if you have something that's left-hand circularly polarized reflecting into a mirror, then it comes out mirror imaged. So you can tell whether it reflected off ice, if it reflected off water, and then you can establish what actually was there on the ground. So that's the interesting thing, which is trying to bring the two worlds together of passive and active users, and without problems between them. Then this is the same thing. This is a picture I took of it's a star trail, but it's a time lapse, and then these are actually airplane trails. But you can imagine that if a satellite's flying over a radio telescope, it will look like this, except in radio, because it's constantly beaconing and it's transmitting signal. And then the problem with this is you have protected bands for radio astronomy. So for example, here, but that's so closely, it's shared so closely with other active bands that the out of band emissions tend to start being a problem. And SpaceX, for example, with the Starlink satellites, they voluntarily decided to give up some of their own allocations so that they don't interfere. So there are altruistic, actions that have been observed in society. So there's methods to. It's not all pessimistic. And then, like I said, there's commercial interference with commercial, which is GPS and Ligado. There's commercial satellites interfering with science, which is the new next generation of geostationary satellites that provide internet with radio astronomy. And then there's the GPS signals which interfere with something called pulsar timing arrays, and which we use to figure out where the Earth is in relation to the galaxy. And it's also radio astronomy. But a GPS signal would dwarf or would interfere with the pulsar signal that you're actually seeking to observe. So, and then of course, if you're doing space science with a satellite, that satellite has to transmit its data clearly, wirelessly, and that wireless transmission itself could interfere with whatever it's sensing in itself. So this is, some complicated stuff that's there. And there's, of course, different people who are regulating this. There's the International Telecommunications Union, which is the international body. There's also various UN, panels and so on. There's different companies. And of course, there's the FCC in the US. And the thing with this is radio spectrum doesn't care, or radio waves don't care about borders. So Canada could have a different standard, and then someone in Montana or, one of the northern states could be adhering to the US standard, but because they're so close to the border, it could transcend and then it could still cause interference, which is another problem that occurs in current spectrum sharing cases. And of course, satellites are not constant overhead, they're moving. So US satellite doesn't necessarily stay only over the United States unless it's in a geostationary orbit. So it's transmitting whenever it's overhead some other country as well. So those are issues. And this is just a picture of geostationary orbit. But speaking of geostationary orbits, that orbit is very special because if you want to be over a particular point in the ground and stay fixed relative to that point, you need to be only in this aforementioned particular slot. And then that's a very thin ring, and it's getting populated by various users. So there's interference between them, and there's interference, the regular interference we talked about as well. So these essentially are your current state. And of course, cybersecurity control, which is if I'm collecting Wi-Fi data at C4C and you're logging into your internet banking, and I'm collecting every single bit of information that's flowing between the phones to the router, it's encrypted, of course, but there is, if I'm doing it at the scale that we are for monitoring baseline noise, then there's a risk that we're actually collecting a lot of this information and it's a security leak. So we need to coordinate with different agencies and also come up with technical measures, not just cybersecurity, but also looking at actual electronics and maybe only collecting statistical information and not actual samples. So these are kind of 4 questions that we're kind of tackling at this point overall. And it's nice to segue off security. I was actually at HCRO, which is Hat Creek. I'll show you a video on the next slide. But on the way back, my aircraft was delayed by like an hour. We were sitting in the aircraft and they wouldn't tell us. They just said it's a technical delay. And being a nerd, and also having, the equipment with me, I decided I'll just tune in with the software-defined radio to the air-to-ground communications and try and listen into what they were saying. And all of this is public, to my surprise. I just Googled San Francisco airport like frequencies for aircraft to tower, and then I just kept flipping through, and then I was just looking out for my flight number there. I want to lie and say I actually heard what my pilot said, but I heard some pilot talk about something. I think I heard about a delay, but basically it's a lot of, it was essentially quite fitting that I was able to use the same kind of hardware that I'm using for my project in my daily life for something that was this simple. Also probably a freaked out some air hostess who didn't know what was going on with some complicated stuff here, but yeah. And of course, if I can do this passively, this is legal. You can listen into air traffic radio. But of course, there's a case where we can do this with other frequency bands where it may not be so desirable. So that's the cybersecurity aspect as well. And I think I'm probably just wrapping up. This is HCRO. It's in Northern California. This is, just me showing off essentially with the trip. And the radio astronomy facility that we're seeking to protect is the Allen Telescope Array. This was actually used for SETI, so which is Search for Extraterrestrial Intelligence. And that is basically a set of 42 dishes. And what they're doing there is they're arraying an individual telescope. So you can see it here. Well, I just let it play. But these are your individual telescopes, and each one of them acts as like one part of a bigger antenna. So the effective antenna size is about as big as they are. And yeah, this was about last month, sitting and doing some light painting. That's a Drake equation, which you can see in my background. And SETI is essentially Search for Extraterrestrial Intelligence. So if you guys have seen Contact, the movie with Jodie Foster, that's essentially what they're doing. They're doing a radio astronomy there as well, but Paul Allen funded the Allen Telescope Array for looking at signals that may correspond to aliens. And we definitely don't want to, in the urge to be connected to each other, humans wise, we don't want to miss out on alien signal. So that's pretty much it in terms of a quick overview. If anybody wants to figure out anything else, any other questions, happy to take them. So any questions?
I have a couple of questions, if that's
Sure.
okay. One, I think you probably answered already, but those hyperbolic maps that you're mentioning about when you're mapping up interference, can you do those in real time, or is there like an appreciable delay?
So what happens here is, in fact, you need to record for a certain length of time. So let me just present this again. In order to actually do the correlation that we're doing, time domain correlation, which is where we're actually recording the voltage waveform versus time, is a little hard to do because light is so fast. So it's what, 300,000 meters per second. No, 300,000 kilometers per second. But yeah, and that's really fast, right? So you need to have a really precise clock, which is another reason we're using the GPS derived clocks. And you need to record for a certain length of time so that you can achieve a good correlation. So what you see here is you see this sine wave. So this is your signal that's actually modulated by some communication signal. And that sine wave, the difference between the correlation peak. So basically what this correlation is actually doing, this orange plot here on the second graph, and I'm sorry, I forgot that you couldn't see it again. So this part here essentially is I take corresponding values. So I take this value here, I take this value here, multiply them, and then this value here at the same location, and then I multiply them and then I sum them all up. And then it's a property that that sum will reach a maximum only when these two signals are exactly on top of each other. And the difference between the peak of this sum and the floor of this sum is determined by the length of the sequence, and also the properties of like how the sequence is modulated. But you can kind of roughly correlate saying that if I have a really long sequence, then the kind of degree of match is either it has to match really, really fine. And then when it doesn't match, it matches much worse. So in terms of real time, coming back to your question, if I'm recording for 1 second, then by definition I need to search across 1 second. So I need to slide say 1 million samples. If I'm sampling at 1 million samples per second, then I have 1 million samples here. Then I need to do that computation with 1 million samples multiplied by 1 million samples and check the sum, and then slide them by 1 sample, slide them by 2, and so on, and sweep them completely with respect to each other. And then it is computationally intensive to do that. Sometimes we do it in the frequency domain as well with spectrogram. And that is another added step of computation. So when I say real time, it's something like near real time. It's about, so on the site for the lightning maps, you can see that it's delayed by about 10 seconds. But
okay, so it's not like hours.
Not hours. So the entire point of this is to be able to detect someone who's transmitting, say, within like 10 seconds of something, and then call them up and say, okay, look, turn your phone off or something.
Okay.
So that's the idea.
Okay, interesting. Also, so another question, I'm just it sounds like, do you have any idea what the main offenders are? Like if we all switched over to Ethernet instead of wireless, would that actually make any appreciable dent, or is the GPS the main culprit?
Yes, Wi-Fi, and so it depends entirely on the frequency that they're monitoring. So at HCRO, at the telescope site, they are interested, the antennas and everything are dealing with a frequency of about a few megahertz, a few hundred megahertz to about 12 gigahertz. And your Wi-Fi is between 2.4 gigahertz to about 2.4 gigahertz, and then also another Wi-Fi band is at 5 gigahertz. So if they're conducting an observation in that frequency range, so if they're looking at a certain region of the sky in 2.4 gigahertz, then yes, you have to turn Wi-Fi off. Otherwise, it'll just swamp it out. In fact, so when you go to HCRO or any other telescope, so HCRO is relatively more lenient, but the Square Kilometer Array in South Africa, which is where one of our partners at HCRO is also doing some work, they don't even have electronics above ground. They have a bunker, basically anything, your laptop, not just for the wireless communication hardware that exists. So it's not just your laptop having Bluetooth and Wi-Fi. It's the fact that currents running in the motherboard, any changing current radiates, which is why lightning is a radiator. So any wire that has a varying current versus time will radiate waves. So your laptop is not a shielded box. There's a lot of gaps in it. So your circuit board, whatever the traces are on a PCB, they act as antennas for some frequency and then they radiate. So that's called EMI, and then telescopes are really sensitive to this. If you, I can pull that up as well. I'm talking, but kind of power levels that they're talking about radio astronomy are mind-bogglingly small. It's crazy. It's got another unit. It's called Jansky, and it's something like 10 to the minus 26 watts, times 10 to the minus 20 something watts, which is nuts. Like your body is giving off 100 watts if you don't have a fever, and we don't. That gives you a sense of how much it is. Like an incandescent bulb is about a 75 watt bulb or 100 watt bulb, and this is 10 to the minus 26. So, and your Wi-Fi power from your Ethernet, from your laptop is easily going to dwarf something that's coming in from space. So, it's kind of probably disingenuous, because another thing that they do with the array is, because you can localize where the transmission is coming from. So they do the same thing. It's the correlation. So if you get a good correlation peak, you can also track where that is, not just tracking the interference. You can use the array to track the source as well. So if the math works out such that it says that the source is about 20 light years away, that's clearly not somebody's Wi-Fi. It's a radio astronomy source, it's an astronomical source. So that's inherently, there is some immunity in the sense of if you're able to actually get a signal. The problem happens when you have your highly sensitive receivers. So imagine someone yelling into your ear. So imagine you have a sensitive ear, right? So then that's what it's like. So you might end up, destroying the low noise amplifiers that are there in the telescope, or not destroying is pretty strong, but you will end up saturating them. And once you saturate them, it's always like, if I'm looking at the data on my screen, it's just a flat line. It's always maxed out. So then I can't do any kind of processing because there's no information in that. It's just completely saturated in my receiver. So yes, Wi-Fi, phones, depending on how close they are, both in frequency and in space, will cause interference. Actually, that's another thing that was in the blurb that I never got around to. The 7D electrospace that I was talking about is precisely this. It's looking at the 7 dimensions are X, Y, Z for spatial location. One is time, which is, time is the 4th dimension. And then you have the orientation, which is the angle. So it's roll, pitch, yaw. Those are the 3 other dimensions. And then you have something called polarization, which is also kind of a vector quantity. So polarization is basically, if you've seen a 3D movie, you know what polarization is, because the glasses, the 3D glasses have opposite polarization on the different eyes. So it's basically electric field oscillating up and down is, say, vertically polarized, but oscillating left to right is horizontally polarized. So if a vertically polarized signal is incident on a receiver that's only sensitive to horizontal polarization, that's fine. There's no interference that way. So if the 7D electrospace is like, imagine it as a phase space, or imagine it as a set of parameters. So if you have an intersection in any of those parameters, then you may have a problem. But if you don't have an intersection in any of those 7, or you could be intersecting, if you don't have an intersection in all of those 7, then you're fine, because you've teased apart the regions in which they're operating. If all those 7 are the same, then you have interference. So location, frequency, and the other stuff, polarization and angle. So sometimes what you can do is, you can see it in my background the other way. So if it's pointing up at the sky, then essentially it's got a really nice fine beam that it's sensitive to, because it's a telescope and it's got a big dish. The larger the dish, the smaller the beam, and the more precise the pointing. So anything coming from outside that region is not really going to be causing that much interference in the telescope. But at the same time, they're really, really sensitive. So even if it's coming in from the side, it still tends to sometimes saturate the receiver. So long-winded answer to that is yes, it's more than just the Wi-Fi and your phones.
All right. Well, thank you. This was a really interesting talk. It's very much outside my wheelhouse.
It's honestly, it's very, very broad ranging. I wouldn't be surprised if there's like something or the other that links to it from this. It's just spanning, getting into it from the last 6 months. The policy implications itself are a pain in. Okay, I won't say anything more, but yeah, and in the engineering as well. So for my PhD, hopefully I do something that pushes like physical limits, novel contribution and all that. But as an industrial problem right now, it's very solvable if people can agree. And the work we're doing is to try and establish a common unambiguous reference so that people can do that. So yeah. And if you're interested, like I showed, you can collect data from your own phone, and I can share a plotting thing, and then you can look at. You can actually do this probably with your phone, and then you can figure out which part of your house is best for Wi-Fi. So there you go.
Oh, I already know my kitchen is a dead zone.
Right.
I'm well aware of this.
Probably a good thing, but yeah. Any other questions you guys had? Oh, and the thing in the background is the Drake equation, which essentially describes the number of civilizations that that we have the chance of contacting. So this is n, and then that's like rate of star formation, fraction of those stars that have planets, the fraction of those planets that are Earth-like, and then the fraction of those that develop life, and then intelligent life, and then communication, ability to communicate. And forget FW for a moment, that's me being smartass, but and then the length of time that those civilizations are alive for. I decided to be show off and add my own parameter because maybe sometimes we don't want to contact ET, because if you've ever seen Independence Day or any of the other alien movies, that's there. But yeah, if you want to follow up this talk with some washing it down with some pop culture stuff, go watch Contact. It's really, really accurate with what's happening. The initial stuff, not the actual travel and contact with aliens, but the initial part where they detect a lot of those terminology. I mean, that's the picture I picked for my blurb as well. It was me in front of the GMRT, which is back home in India, which is another radio telescope. And there's a scene in which Jodie Foster is wearing headphones and acting like she's listening to the actual receptions, which is what I was trying to go for. But yeah, that would give you a kind of flavor as to what they do over at HCRO.